Okay, good morning, everyone. Welcome to this fourth day of this conference meeting. So the first speaker is online. This is Arnaud Cassan from the Institut d'Astrophysique de Paris. He will talk about the microlensing mass measurement from the long baseline interferometric observations. Arnaud, are you online?
Yes, I am online. Thank you very much.
Yeah.
So I think I can start.
Yeah.
Share my screen. Voilà. Can you see my screen?
Yep. Yes, we can.
So it's a pleasure to be here to give this talk. I mean, not to be here, to be online. Of course, I would have preferred to be there, but it was not possible for me this time. So I will talk about an observation we did in with a long baseline interferometry. We have been monitoring a microlensing event. And I will, in this talk, I will show you what was the goal of this observation, how we made it, and what are the implications and the perspective of this kind of observations. So here you see on the first page the different collaborators in this project. So first, let me just say a few words about what is gravitational microlensing in the Milky Way. So here we are in the Milky Way, the Sun, and of course. Observing here, and during what we call a microlensing event, by chance, a lens, which can be a planetary system, which can be a normal star or a black hole or a stellar remnant, crosses the line of sight of a distant star, which we call the source star. And during this phenomenon, of course, the light is bent by the lens, and what we receive is a flux which is modified by the presence of the lens. So basically, what we observe is usually is a magnification effect, which means we receive more flux from the source that we would receive without the lens. This is what we usually do when we do photometrical monitoring of microlensing events. So I have a second slide, which just give a few important facts that will be important for the following of the talk. Is the case of the single body microlens. So in case you have the observer is there, you have the source star, which is the normal star usually in the bulge, or in this case it will be a bit outside of the bulge, but it's a distant star. And the microlensing star, which is isolated in this example, is here, and you see that it bends, of course, the light in this way. And in this case, you have only two images that are produced, which are here. And the important thing to remember is that you have two images, which is here shown in red and blue. And the most important point is that these images are usually arc-shaped, and you have two images which appear. The source, which is in orange here, you don't see it anymore, of course, because you don't see you see only the two images. And what is important is that the two images are aligned with the lens and the source. So if the source, which is there in projection, travels with respect to the lens, which is usually dark, but sometimes you can see it. It doesn't have to be luminous, that's the point. You see that if the source travels relative to the lens, then you will have a rotation of the two images. The magnification effect comes from the fact that the surface intensity is conserved, which means that if the image had exactly the same surface as the source star, you would receive exactly the same flux. But as the two images in total have a higher surface than the source, that's why this is where you get more flux, and this is where you get the magnification effect. Voilà. So we will have to remember this slide, this scheme, because it will be important for the following. Voilà. And if the source is perfectly aligned with the lens, then you will observe something completely round, which is, of course, what we call the Einstein ring. Okay, so this is our important facts about what we will discuss. Voilà. So now coming to the microlensing event, Gaia19bld. So this event was this microlensing event was actually alerted by the Gaia collaboration. I mean by the Gaia satellite. So these are in this plot on the left. These are the red losange, the red square, and in April 18, it was recognized as by the Gaia Science Alert team by a possible microlensing event. And then you see that you have from the ground a very dense follow-up, photometric follow-up of the event that is starting to try to discover the nature of this increase of light and this variability, and at the end model it and to see what kind of lens it is. So as this event was very bright, it's one of the very, very bright events. We have a few of them in per year. It has been recognized as a potential target for interferometric observations. And in our program, we are with a pioneer at VLTI with the auxiliary telescope. We can go to H equal 7.5. And this was predicted to go beyond it. Voilà. Actually, on the right, you see the zoom of the light curve when the event was over, and you see also the timing of what we did with this event. So 8th of July, we recognized it as a potential target. In 10th of July, we triggered our target of opportunity on the Pioneer, and then we were lucky that some people observing gave us some time to monitor the event, and I thank again these persons we are acknowledged in the paper. I put the reference at the end. So after the trigger was sent in 10th of July, we managed to obtain 3 epochs: 12th of July, 19th of July, and 21st of July 2019. And actually, they were just above, as you see, the Pioneer limit in H, and all these data were of very good quality. And we actually got another data, another set of another observation there, but we just could not get anything out of it. Was not did not observe any fringes, and that's really confirmed that this was really the Pioneer limit. It was interesting to see. So we got these 3 observations really at the peak of the event, and you see that the shape of this curve at the peak means that we resolve the size of the source, which means the image should be elongated and makes be arc-shaped. But before we observed it, we had no idea, because we had many real-time modeling that had different possibilities, but all of them were converging, even before the trigger, that we would expect a peak between in this region. And then we observed this, what we call finite source effect, because we resolve the finite size of the source. Voilà. So these are the data we got for the 3 epochs: 12th of July with a median baseline configuration, 19th and 21st of July with a large baseline configuration of the VLTI and on the auxiliary telescope. And when we did it, it was really not clear what we were observing, because we didn't know the nature of the lens. So all the scale you see here depends on the mass of the lens. And it can be very different if you have a normal star, if you have a black hole, or if you have a lens which is close or a lens which is far, because the mass and the distance of the lens are mixed. I mean, so we don't know exactly. So at the end, where we really made some first detailed look at this data, not yet at the visibilities individually, but just at this very simple non-parametric reconstruction, it appears that actually the signal is contained in this small blob, as a collaborator said, small blob. And the question is, of course, how will we analyze this data? Because if you just use some normal standard pipelines with, for example, two point images, then you don't fit anything. So we had to develop some interferometric microlensing model to deal with this new data that has never been modeled before, actually. So here is one of the results of the fit. So If you assume that the lens is, if you assume that the image are arc-shaped, which is what we expect from the microlensing event, then you see that you can fit all the visibilities. So on this plot, on the middle plot, you see the data of, I don't remember which, maybe one of the epoch only, but for example, yes, it's written here, 19th of July, and in 19th of July, we actually got two sets of data. So that's why you see these two plots. And in the meantime, the lens has moved a bit, so it's not exactly the same. You see, even if it's quite close. This was 11 in the evening, and this is 11 and 30 minutes. So you see that it has changed. So it's really changed very strongly when you are at the peak because the image rotates fast. So here you see that here you see the visibility, the squared visibility, and the observation are all the points on it. If you would assume that the lens, that the image are not arc-shaped but point-like here, then you have this classical, very simple pattern, but you don't fit at all the data. So what we have done is that we first took the three epochs and fit them independently without any timing of how we would expect the image to rotate. And I don't show it here, but it's extremely interesting that you really get a very strong constraint, even with only one epoch, about that the images are shaped and what are their orientation in the sky, which means they are really in this direction. So these are the three epochs, 12, 19, and 21st of July. And you see that in this last epoch, 21st of July, the event was already faint, and we got only one data and not the second set of data. But what you see here immediately is that it's really the image has been rotating a lot during the event. And what you see here is that actually this one has moved like almost 120 degrees here, like this. And the visibility are very different, so that's why you have very strong constraint on how the lens has moved. And also what you measure very precisely is actually the overall size of the Einstein ring, because this data, the data is spread more or less depending on the size, the actual size of the Einstein ring. So here the unit is a bit strange for interferometry because it's really like UV, but it is also normalized with the Einstein radius, because the model of the microlensing event is given in Einstein units. So it's an angular unit in milliarc seconds, for example, and so that's why we basically can compute the model easily in inverse Einstein units, and then you scale the data you get with the actual value, and you measure the value of the Einstein radius by scaling the position of this data to this what I call the UV Einstein plane. So that's why it is also in this strange in this theta e minus to the -1 units. Voilà. So all fits very, very well. And I have to say that in this series of image, it is not, I don't see the fit independently of this one independently of the others, but this now, the trajectory of the source is not free. It is a trajectory which is straight trajectory with a time scale and speed and etc. So, and you see that the data fit very well, even if you say that the lens move together, and this you exactly predict what you observe. And that means that you will have very strong constraint on the Einstein ring and also on the direction of motion. We'll see it later. So I just show this quickly, which are the closure phase. So you take three telescopes among 4, and you compute the closure phase, some of the phases. And of course, as the images, as you see here, it's a bit complex on the right. Unfortunately, I don't have time to detail much. But let's say S1, which would be a source, unseen source at S1, and you have, in this case, the image red here and the blue here. You only have 2 images. And you see that they are quite symmetric. So that's why you don't expect the closure phase to be very, very high. But still, as with three epochs, we have a degeneracy between the trajectory which go east, north, or west, south. And you see that here, actually, even if the data are not very symmetric, we can see a difference, which is not very, very strong, but with a model, the finite model that we know which direction it is, because we know by parallax, I will talk a bit later, it is even the closure phase are compatible with this, and the preferred model is a black one, which is one of the trajectory here, and the northeast trajectory. But of course, it is not a very strong signal in this case, but it is perfectly compatible with what we get later. So here are the series of the three images. These are not the scale, the red scale are a non-parametric reconstruction. So this time it is done with the squeeze software, so they are independently. So it's non-parametric. So each epoch is reconstructed independently of the others. And in white, you see the model which uses the interferometric visibilities and the closure phase, and in white, and what would be is the prediction of, and you see that it is extremely very, very similar. And even you measure actually not only the direction of the images, but you also fit the width of the images. You see, not the small, I mean, the width of the image, you see that here, it is smaller than here, for example. So it's very, very impressive. So it's the first time, actually, we observe gravitational arcs in a microlensing event that we can reconstruct images. So there have been a previous measurement of interferometric measurement of a microlensing event in previously, but only closure phases could be used actually, and we show later how is that even in this case you get very good results. But in this case, we were really able to reconstruct for the first time the arcs of a microlensing event, and so these images are rotating, which is the only case in any kind of microlensing event where you see actually the image rotating. So it's really nice. So you can click here when you have the presentation. You can go here there and see a movie of what the event, what happens, and when the data were taken. So I don't have time to show it here, but voilà. So now we would like, from this kind of observation, we want to measure actually the mass of the microlensing event and the distance. But since the distance and the mass are combined, then if you measure the mass, you will measure also the distance. So we will just concentrate to the mass here. So the mass is given by this very simple formula, simple formula, which is theta e divided by a constant time what we call the microlens parallax. So theta e is the Einstein ring radius in milliarcseconds, and this is exactly what we have been measuring with interferometric data actually. So this is which is known. Maybe I'll give you later the value. I will give you later the value, but this is measured at very, very high precision by interferometry. So the only part missing is the parallax that we want to measure. And perhaps this feature is a bit complex, but let's go to this line, this black line. You see, the lens is the violet point in the middle, and the source is a black one. So the source, by chance, is there. Voila. And it has two images, which are the two blue images along the line. We have seen that they are aligned. And this is what you would observe at a given time. But if you observe from another point of view, which is the principle of parallax, for example, from space or another point of Earth, or you wait for some time, then you would see this point, the source, you will see it there. Because if you look at, you put the lens at the given place, if you change observer, then the source will appear somewhere else. And so you will see a different combination of the two images. So this will give you an information about the geometry, which means that you will have an information about the value of the Einstein radius, because this separation will also depend on the actual size in milliarcseconds of the Einstein radius. So if you measure the event from two points of view, you will measure some parallax that will give you an important information on the mass. Voilà. Alors, so actually there are two points of view. What we have done with Pioneer, which is which is something new actually, and another thing which is new, and I will show you that this event has been observed also with the Spitzer by space, and you see that everything is very, very consistent. So without going too much into detail, here you see the trajectory of the source relative to the lens affected by parallax. So if there was the Earth was fixed, then you would see a straight line, but it's moving. So you see this trajectory, which is a bit warped, changed. And in black, you see where we got the interferometric data. So what is very important is that since you remember that the image in the sky are moving and you have a very strong, you know exactly how they are oriented, you can reconstruct the trajectory, the angle of the trajectory angle, so which means in which direction the lens the source lens, the relative source lens trajectory is orientated, the orientation. This is what you see here. And in gray, you see that this is the angle, trajectory angle. And in gray, this is the constraint we get with Pioneer, with interferometric observation. So at the end, it's very constraining because the parallax can, if you don't have this information, it can be anything. You can have any kind of movement between the lens and trajectory. But here, it's a very strong constraint. So even if you give only this constraint, you get here in this plot, you get the gray line, which is you have a parallax measurement in north and in east here, and the constraint is north is a kind of position in the direction in the sky. So if you constrain the direction in the sky, you will have like this kind of lines, which are the constraint from interferometric observation with Pioneer. And if you use only the photometric light curve, then you get the blue curves, which were actually off because at the end, there was a lot of work for the photometric data because so we had the Pioneer data. So everybody really tried to do the best with the data, knowing a bit. But Pioneer has always been completely independently fitted by. It's completely independent of the data. Yeah, of the photometric data. And if you combine the light curve and this simple information about the very, very precise information of the angle, you really get a very strong constraint on the parallax. And now let me go very quickly to this slide where I show you the light curve that's been observed by Spitzer. So since the point of view are different, the light curve will be different. And then from this, you can also put some constraints, which are the blue one. And at the end, you see that the constraint you obtain from Pioneer alone with the light curve and these 2 points of view with the space satellite and Earth, you find exactly the same result, which is very, very impressive. And also, it has been actually possible to test some new method to deal with space data, which are a bit dangerous because they don't apply all the time. But this time, it shows that these data are very similar. So at the end, we measure to a very good precision the parallax with just what I have shown you. So here you see Gaia, this event is there. This is the relative precision of measurement of parallax for many microlensing events. And you see it's not the best that has been done because actually the parallax has not been very, very well measured for this event because the photometric data was not maybe perfect, let's say. But we already got a very good measurement. And this is exactly the same we got with Pioneer, interferometric and space parallax. So it was, and since Spitzer has stopped operation, it was extremely important to have this test of robustness, which shows the power of interferometry. But of course, what is extremely impressive is the precision you get in theta e, in the Schoenring radius, and you see the data here are much smaller than all other microlensing events. And the microlensing event Kojima one you see here actually is the one that has been monitored by gravity at the VLTI. Also, where the closure phase has been used to constrain the southern chain radius, but it was a bit dependent of the model. In our case, it is completely independent of the photometric model. And finally, you get the mass here, and it is the most precise mass we have been measured in microlensing events so far. So here you have the different the values. Voilà. So that's my last slide. So what we want to do is increase increase the number of events. And what you see here in this bit complex plot is that when you increase the magnitude of the target, you get many more events. So for example, here, and I will conclude, here in this, we have made some simulation about now if you don't want if you accept the microlensing event to be a bit fainter, but you have a star which is close by, so at few arc seconds, and is brighter, which is correspond to the dual field wide mode of gravity, this new mode, then you don't have only a few events per year, but you have many events per year, which give a wealth of events where we can choose very interesting event, planetary system or black holes, for example. So this is my summary. So with Gaia19bld, we have obtained the most accurate angular engineering measurement ever obtained, independently from the light curve, and also the most accurate mass measurement. It was actually limited by the parallax and not by the measurement of theta. Future interferometers will provide many more targets because it will, of course, decrease and we have fainter events. And the main perspectives is we want to measure the mass of exoplanetary systems and also measure the mass of isolated stellar mass black holes and other stellar remnants at a very high precision. Thank you for your attention.
Thank you very much, Arnaud. Very interesting talk. Any question from the audience? If not, I have a question for you. Can you hear me, Arnaud?
Yes, I hear you.
Yes. So I was wondering, you mentioned that the last point that you were planning to do with Pioneer was not, the event was not bright enough. What would this point bring to the result if you were able to get it?
Actually, actually nothing, because if you get only one image, you should get theta e, the engineering radius. If you get two epochs, then you have a degeneracy between this trajectory and also some other trajectory which will be perpendicular. And if you get three epochs, then you get only this only one direction in the sky. And if you get the parallax, it's obvious that it cannot be so if I show you here, you see, sorry, on this plot, if you would have and the trajectory which would go northeast or west-south instead of northeast, the point would be completely here. It would be many sigma out of the constraint from the light curve. So at the end, if you get three epochs, you don't need more, unless of course you want to get better data, of course, and you want to see there are some systematics, etc. But apart from this, theoretically, with three epochs, you completely independently from the light curve, you measure exactly you measure exact. Wait, okay, stay here. You measure exactly all what you need, the engineering radius and the direction. So, and if you have two epochs, then you may have another network of another constraint, which would be something like perpendicular to it. And then it would depend if it would make some degeneracy or not with the constraint from the light curve. So at the moment, what the strategy we are doing is to restrict to two epochs, not three, but two epochs, because we think that we will remove the degeneracy with the other set of territory like this or like that with the light curve actually.
Okay, thank you. There are questions on Zoom. Question from Passionate Sarah: to improve the parallax, is there any prospect of target of opportunity observations from a satellite like TESS?
Okay, so if in fact yes, the answer is yes. Of course, I don't know exactly what TESS could do in terms of magnitude and things like this, but if when you see a microlensing event in direction of the bulge, more or less, if you have enough distance between the satellite and the Earth, of course, then you will get some parallax. But you need to have an alert system when the event increases, and you need to trigger an alert to observe the microlensing event during the peak, because, and also in the baseline, because this is where you would get this the information about the difference in the light curve, and that will give you some information on the parallax. Wow. So the answer is yes, theoretically, and then is it possible to do it in terms of alerts, in terms of time series and of magnitudes? Yes. But I have not looked at this, so I can't say.
Okay, last question with a quick reply because we have to move on. Question from Jinhua He. Are the arc lengths well constrained and agreed to expectations?
Yes.
Okay.
Yes. This is so. Yeah. Okay. The answer is yes, and you voila.
Okay. I think
perfect. Actually.
We should move on. Yeah. Thank you again.